All right, you should be able to hear me okay. We're going to start this. Actually, I better close this window. We're going to talk about LeChat and his principle, or in other words, disturbing a chemical equilibrium. There's lots of things that can disturb equilibrium. Really, anything you do to the reaction. We're going to do a bunch of things to a reaction on Monday during our lab. But if you change the temperature, change the concentration of anything, or change the volume. Of course, changing the volume only works in gases because with solutions it would not change the molarity because you'd be taking out some of the solute as well. Well, anyways, LeChat says that, in short, if you change equilibrium, the system's going to do whatever it can to shift back into equilibrium. So it'll get itself back to the equilibrium it needs to be at. Now, if we look at some examples of that, temperature. If we change temperature, first we have to know the enthalpy, the delta H of the reaction. Again, you're going to notice things that we do keep coming back and back and back. If you change it in the exothermic direction, and so in exothermic, if you take the temperature and we lowered it, K will change. In the endothermic direction, when temperature is raised, K will change. It's going to depend whether it's endothermic or exothermic as to how heat's going to affect it. Remember, exothermic reactions means heat is exiting a reaction, and an endothermic means heat is entering a reaction. So we really, when we do LeChat, we almost think of heat as being a product or a reactant. In an exothermic reaction, heat is like it exits, it's a product. In an endothermic reaction, heat enters, it's a reactant. When you change concentration, well, if the concentration A goes up, B has to go down, and C and D will also go up. The reason being is if there's more A, there's more of it to react. Therefore, it's going to consume more B, and when A and B react with each other, they're going to make more of C and D. And again, equilibrium will always shift away from a concentration increase. It'll always shift toward a concentration decrease. But since temperature doesn't change, K will stay the same. That's why the concentrations have to change, and we're going to look at that mathematically a little bit at the end as to why that's true, why that statement has to be true. We can actually prove it with some numbers now that we understand equilibrium expressions. Gases, this is where it can be a little bit more difficult for students to understand, because with a gas, you can't remember a simple rule. Those of you in first period, you can think back to Bailey's video where she had all her rules. Well, there aren't those steadfast rules for predicting equilibrium for a gas system, because it's dependent on how many moles of gas are on each side. So you got to look at both. This side has 2 moles of A and 1 mole of B for a total of 3 gas moles over here and only 2 gas moles over on this side. So for this reaction only, each reaction it's unique. If the volume goes up, that in essence means the pressure is going to go down. We have more space for the molecules. Well, if the pressure goes down, the reaction, according to LeChat's principle, obviously the reaction's not really thinking this, but the reaction's going to want to, we as the outside factor, we decreased the pressure. The reaction's going to want to increase the pressure. Well, it can increase the pressure by allowing there to be more moles of gas. So it'll shift to the left where there's 3 moles of gas, which will help to increase the pressure in the container. Now, realistically, what's actually happening is if you have a larger volume, it's harder for A and B to bump into each other and have a reaction. Thinking back to kinetics and collision model, the bigger the volume, the more difficult it is for these two to find each other to make little baby 2C. So therefore, on this side of the reaction where you only need a C, it can obviously break apart, decompose at any time to an A and a B. Yet at the same time, if you decrease the volume, therefore increase the pressure, you're going to give A and B a better chance of running into each other. The reaction's going to, we decreased the pressure, or increased the pressure, by decreasing the volume, we increased the pressure. So the reaction's going to want to decrease it, and it's going to decrease it by going to the side with fewer moles. Again, really what's happening according to collision model, by decreasing the volume, you're giving A and B a better chance of running into each other. Temp stays the same though, so K stays the same. They just have to balance out to keep K that same constant. Now, just as something interesting, the Haber process, which is a very, very important thing for agriculture, a way to synthesize ammonia from nitrogen and hydrogen being the most abundant element in the universe, nitrogen being the most abundant element in our air. But the weird thing is, those of you who have been in biology probably know, nitrogen in the air is almost worthless to us as living creatures, not just humans, but all living creatures. It needs to be fixed somehow to something to be able to use. One of the best ways to fix it is to get it into an ammonia compound, because that's the start of an amino acid. Well, they figured out naturally at room temperature, 25 degrees C, that'd be room temperature. K is 3.5 times 10 to the 8th. So you'd at first think, oh great, that equilibrium is very product favored. This is good news for us. It also is an exothermic reaction, meaning that it's going to become more stable as it makes NH3. But the problem is the reaction, we don't have a rate here, but if we had the rate, the reaction is really slow. It is product favored, but you'd sit there and wait for years and years and years to get the ammonia. Just like the rusting of iron, it's product favored. Eventually iron will completely rust, but it takes a very long time for it to happen. What Fritz discovered was that if you increase the temperature, well, then you got an issue. Since it's an exothermic reaction, temperature would be on the product side. So by increasing a product would shift it back towards the reactants. So you're like, well, we got to increase the temperature to speed up the reaction, but since it's at equilibrium, it actually does the exact opposite. It makes K go down and therefore makes it not go as fast as you'd expect. What he figured out is that if you increase the pressure, you play with LeChat's principle in two directions. You have to heat it up to get the molecules moving fast, to give them enough energy to get over the activation energy, but yet you pressurize it enough to force these N2s and H2s to collide with each other to make NH3s. He won the Nobel Prize. You win the Nobel Prize, you get $1 million, along with all kinds of other great stuff that goes along with it. And then, of course, later on, people have discovered catalysts that can speed the reaction further. That's just a little chemistry tidbit for your Saturday morning or Friday evening or Sunday or whenever it is you're watching this. Probably made your day just that much more exciting. Let's look at an example together, though, to actually see mathematically how this works. Now, total side note, those of you who are artists, this Smooth Draw 3 is a wonderful program for drawing. If you like to do digital drawing, it's got all kinds of options. I can even, to cheer up our mood, put a butterfly in here. Wait a second, there's our butterfly. All kinds of different stuff you can do, but it's really great for artistry work. I'm going to switch back to my felt tip pen, and we're going to look at chemistry, which is an art, obviously. But we're looking at this generic reaction that has a delta H of positive 48 kilojoules. Again, making it an endothermic reaction. It's endothermic, which really means, oh, now my butterfly is there in the way. I need to go ahead and erase him. We'll put the butterfly somewhere else to brighten our day. But what that means is heat is acting as a reactant. So heat is over here. Now, I could just write the words heat like I'm doing here, or I could put in here 48 kilojoules, either way. So first thing to think about this equilibrium, if I increase the temp, so I'm going to increase the temperature. K is going to change. The K value is going to change. But if I increase the temperature on this reaction, by doing so, increase the temperature, I'm literally adding a reactant. Heat's one of the reactants in here. So if I increase this, I'm going to give more A's and B's a chance to react with each other. Therefore, I'm going to make more AB. So I'm going to shift to products. Shift to the products. So I've shifted to the products. This is probably a poor choice in pens. Let me try a different pen. Just a regular pen, not a felt tip pen. Well, that's a little big. All right. Anyways, so that's the first thing. By having a positive delta H, heat is a reactant. If it was a negative delta H, heat would be a product. I'd put heat over here plus heat, but it's not. That's why I wrote delta H right there, because I knew I wasn't going to have to put heat right in that spot. Well, that being said, let's go ahead and erase this guy, get him out of here. We can see that that's clearly true. probably a better way to do this. I bet I could probably use that selector tool, but hey, this gives it more of a real feel to it. But now let's pretend I increased A. Well, I'm going to start out with an initially. Think about an ice table here. I'm going to initially say I've got 0.1 molar of this guy, 0.1 molar of this guy. Well, I'm going to not say initially. Let's say at equilibrium. At equilibrium, I've got for this compound 0.1 molar of everything. Well, based on what we're looking at, assuming that they're all aqueous, K would equal 0.1 squared over 0.1 times 0.1. Now I chose this purposefully because that means K at this given temperature, whatever the temperature is, K equals 1. 0.1 squared over 0.1 squared is 1. So my K value is 1. That means the ratio between, at this temperature, the ratio between products and reactants always has to stay at 1. Well, that's true. That's a must-have thing. So what if I added some of B? I added another 0.1 molar to this situation, or 0.1 moles, however we want to think about it, of B. Well, now K has to equal 1, and it has to be some value X, whatever this is going to be, over 0.2 for B2, 0.2 times the new value for A. We'll call it Y. Well, mathematically, if we think about this, for this to be true, and still stay 1, X has got to grow. It has got to get bigger than, greater than 0.1, and Y has got to shrink. It's got to be less than 0.1. Meaning if I add some of B, I'm going to have to make more of this guy, and I'm going to have to lose some of A. So in other words, by adding some of B, I will shift towards the towards the products AB. If that didn't make all that much sense to you, that's okay. I just wanted to show mathematically why that had to be the case. To make this true, X would have to be greater than 0.1, and Y would have to be less than 0.1 to, again, make these be the same truth. Because if they were both 0.1, this would no longer be true. It wouldn't equal 1. So to make it equal 1, we could, of course, solve that mathematically if we wanted to. I don't really want to go through the trouble to do it because we could do a nice table just like we have before. Let's look at some other examples just to make sure we know what's going on here. We've got our reaction here. And it's asking us if we decrease the concentration. Let's see, why isn't that pen coming up? Should be able to write with a pen. Oh well. It doesn't want to allow me to use my pen. So we'll just look at them together. If I decrease the concentration of dihydrogen sulfide, I take some of this away. I take it out of the reaction. Well, by doing that, to keep K in balance, I'm going to have to make more of it, which means my reaction's going to have to shift to the left. If I increase the pressure, well, we add up our moles of gas. I've got 3 moles on this side and 5 moles over on this side. If I increase the pressure, that means the reaction's going to want to decrease the pressure. The reaction can decrease the pressure by shifting to the side with fewer moles, shifting towards the reactants. Again, talking about the real reason that's happening, it's because you're making these 5 molecules, giving them a better chance of running into each other. If I increase the temperature of this reaction, I have no idea what's going to happen because it doesn't tell me a delta H. I'm going to need a delta H to be able to answer that question. It's actually a really bad question, I guess. Now, the thing I do know is if I increase the temperature, this is going to change K. These won't, but changing the temperature will change K. If I increase carbon disulfide, here's carbon disulfide. If I put more of him in the reaction, I let more H2 react. If more of these things react, I make more of these reactants. Again, they're called the reactants, even just because they're on the left side. Anyways, I'm going to stop now. I've rambled along enough. Edmodo has some links to do some practice. You've obviously got your homework to do some practice. Best of luck.